Okay, let's, so I made this web work due tonight at 5, so we could have extra time after we discussed. That was intentional. I gave you unlimited attempts on the problems. That was unintentional. So enjoy it while it lasts. So let's talk about this one. So the first thing is, I hope you saw my note on Blackboard, that when you have something like this, when you have a line integral like this is essentially what? What's that right there? P, that's P. And this is? That's Q, because we're doing P times d of x plus Q times d of y, so that's dot product, right? That's the dot product of PQ and dx dy, which we know when we solve it, it's dx dt, dy dt, dt. This is the same thing, it's just the vector dx dy. So this form, I tried to alert you in the announcement that this form is just our dot product, it's just f dot dr, right? That's just f dot dr, just written in a different way. Okay, and so there's that, and then, oh, we're heading in homework, yes, heading in homework. Make sure the heading correct. Is our heading? Okay, can you do that without talking now? Hand in the homework without talking? Okay, so then, can you stop talking, please? Can you stop talking, please? Thanks. All right, so notice that here's the key here, non-closed path. So I'm guessing many of you missed this because you didn't notice this is a non-closed path. They're asking you to evaluate the line integral from A to D. Just A to B, B to C, and C to D. Okay? If you tried to do that just by evaluating the line integral, I'm guessing that was ugly and bad. Okay? So then you say, is there an easier way to do that? Is there an easier way to evaluate this line integral? Okay? And so since this is the web work on Green's theorem, maybe it has to do with Green's theorem, which is not mentioned here, but you have this kind of added bonus that we're talking about Green's theorem. So let's write out what Green's theorem is. Green's theorem says that the circulation line integral, and what is C? What kind of thing is C? It's the boundary, and then what kind of thing is C? Simple closed loop, right? It's a closed path, right? So it's all the way around our region, which we call D. And then we know we evaluate Qx minus Py, and that's going to make more sense today. Why we do that? So here's Green's theorem. So is the path that they're asking us to find the line integral for, is it a simple closed loop? No. So how is it that we can use Green's theorem? So don't answer, just think about it. How is it that we can use Green's theorem to help us do this? So what is a loop? What would be a simple closed loop if we also returned down AD, right? So just as a hint, this closed path could be the line integral, say A through D, right? So A through D, f dot dr, then what? In order to get this closed line integral around this closed path, we could think of it as the line integral that we want. No, this closed plus the line integral from D to A. And that would be the closed loop. That would be the closed loop all the way around. and that would equal, now you have an enclosed region D if you go all the way around. So this is what? This is the line integral you're asked to find. If you include one more segment of that, then you have a closed loop, which then would equal the double integral over D of Qx minus Py. And what are you're trying to find just this much of the closed loop. So that's my hint. That's a really, really good hint, right? That's a really, really good hint. Any questions on what I just explained? So the line integral from A to D plus the line integral from D to A, that gives you a valid kind of left-hand side of Green's theorem, a full closed loop integral. And so then that would equal this. But the integral they're asking for does not equal this because it's not a closed path. Okay, any questions on that? And so then you have till 5 tonight to finish up the web work. Okay, cool. So let's just look at a couple more Green's theorem examples and we'll move on to new stuff. So this was from your the review. I don't know if you remember doing this on the review, or maybe we didn't, because we hadn't done line integrals yet. Okay, so this says find the circulation line integral if C is a simple closed path through the vector field 1x. So what does the circulation line integral entail here? What does it entail doing for this particular problem? We're going to find the circulation line integral. We'd have to do 3 parts, right? We'd have to parameterize this little parabola y equals x squared. And we'd have to parameterize the horizontal segment and then the slanted segment. And we would have, so we could call this site, say, C1, C2, and C3. And so we could say that the circulation integral would be equal to C1 we'd have to break it up, right? C2 Make sense? So that would be that. And so when we ask the question, I don't want to do 3 integrals. Is there an easier way? Is there an easier way? So I'm going to leave that to you. So you need to find the value of this. It does not say you have to do this. It just says you need to find the value of this, right? So it just says you need to find the value of the circulation integral around this path. So this equals this, but the problem does not say that you have to add up these 3 line integrals to do it. It's just find the value of this. Go while I take attendance. So who had an epiphany here? Yeah, Eric. Why? Okay, so back up. So why are you talking about Qx and Py?
I decided to do Green's theorem.
Okay. So Green's theorem means what?
It's going to be the double integral over the region Qx minus Py dA or times d.
Can we use, does it set up for Green's theorem? Can we use Green's theorem for this? Yeah. Sure. We got a closed loop around a region D. Okay, and then you said, so now you're going to evaluate this double integral. So tell me about it.
Qx was 1 and Qy was 0.
So 1 minus 0 gives 1, okay.
And then I did second type 2, so I did dx dy. So dx from negative y to square root y.
And why did you choose type 2 over type 1?
Because type 1 you'd have to do 2 separate
So he's saying if you do dy dx, then you'd have to do 2 double integrals. Agree with that? Everyone see that? That the bottom is different. Over here, your bottom function is different than this. But if you do type 2, it's the same left and right the whole way, right? Okay? So how would someone else take it over for that? So if it's just the area, right, it's just the area, then why do we need to do the double integral? Right? Isn't it? It's the area of D. It's only the area of D because we end up integrating 1. So do we have to evaluate the double integral? Yeah, so this is parabolic. So we don't, in the back of the geometry book, there's not a page for parabolic triangular regions, right? There's like not a formula for that. Okay? So this is not a common, this isn't circular, it's not straight. So because it's parabolic, we kind of need to do the double integral.
Could you just find the area of what that circle would be and divide it by 4?
It's not a circle, it's parabolic. That's the thing, it's not circular. Yeah, if it were circular, absolutely. If this were circular, then we could, this could maybe a quarter of a circle and plus a triangle, absolutely. But because it's a parabola, who knows what that means for area. So that's why we need the double integral. Okay, so someone else take over on our limits here. So what'd you get for limits? So we're just going to do dx dy.
Negative y to square root 1.
He wants negative y to square root of y. And then from?
0 to 1.
Okay, and so, Paul, you raised your hand. Agree with that?
Yes.
Yeah. Good. And then anyone get an answer?
7, 6.
You should get 7, 6. And that would be the same as if we broke this up into 3 line integrals and added those up. We should get 7, 6. We're not going to take the time to do that. So we approach this, find this line. We're asked to find this line integral, and we did it by finding this double integral. So what did? We used Green's theorem. All right? So if you had just directly found these 3 line integrals and added them together, that would have had nothing to do with Green's theorem, right? That just would have been evaluating a line integral. So if it says use Green's theorem, that means that you're going to do something else besides what it's telling you to do. And then by Green's theorem, they're equal. Does that make sense? Okay. Questions on this example? Okay, so last example is this one. So here's this slanted ellipse, x squared plus 3xy plus 4y squared equals 1. See that over here? And it's asking us to evaluate the line integral around that slanted ellipse. So we certainly could try to evaluate that line integral, or what else could we do? Green's theorem would say that that thing is equal to double integral of closed region of qx minus py dA. So let's talk about each of these. How about doing it this way? So it doesn't tell you, it just says evaluate this line integral. So we could try to do the line integral, or we can try to do the double integral. So how about doing the line integral? What do you think about that?
Is it conservative?
Is it conservative?
Looks like it's bad.
Qx equals
2y.
2y. Py equals 2y. Okay, you weren't supposed to notice that right away. Okay? And we were supposed to talk about the fact that this line integral of a slanted ellipse is easy or hard? Terrible. And then the double integral of a region inside a slanted ellipse is easy or hard? Worse. Okay? So then we say, how in the world are we going to do this? And then you notice that this is conservative. So good job, Alex. So this is conservative, and then we say, phew, right? Don't have to do these terrible things because we just know that this circulation integral is all closed loops in a conservative vector field amount to 0. Done, right? So when in Green's theorem problems, always check for derivative vector field, okay? Because then that will make the problem end quickly. Except for the example we saw at the beginning of class last time, remember? So we're still that's still an open question. We're still trying to figure out what's going on with that one, okay? But in general, if you have a conservative vector field, you know that the circulation integral is 0, and that makes a trivial case for Green's theorem, right? Both sides of the equation are 0. Okay, so let's talk about regions. So we've been talking about this closed regions D for these Green's theorem problems. So let's be more specific. A connected region, the idea is the region consists of one piece. That's the idea of a connected region. You just have one piece. So that's connected. So if it's not connected, it's not one piece, right? It's not one piece. So the formal definition then would be, given any 2 points in D, given any 2 points, there exists some path from A to B, that lies entirely in D. All right, so that's what the formal definition of a connected region is. So given any 2 points, say A and B, in D, does there exist a path such that every point on the path is in D? Right? So that's easy, right? So if it's connected, that means you can get to any point A to any other point B by staying in the region. That's connected. So now what about this? This is not connected. Do you see how it violates the definition? Is there a way I could pick an A and a B so that I can't find a path from A to B that stays in the region? How would I do that? A here, and then B here. So if I pick A there and B there, then there's no way I can draw a path from A to B that's entirely in the region, right? I have to leave it and come back in. So that's why that's the formal definition for a connected region. Okay, does that make sense? But so the idea is just that it's one piece. It's one piece connected, right? Connect is good terminology for that. Okay, next one is simply connected. Simply connected means that it's one piece connected, but there are no holes in it. Okay, that's what simply connected is. It's one piece with no holes. So like if I came up here and I made a hole in this over here. Would it be connected? So now there's a hole. There's inside that red thing, that's not D. D is only what I've shaded blue. Is it connected? Yeah, it's still connected. You see that any point A and B that you pick in the blue shaded part, you can get to by staying in the blue shaded part. Okay? So then simply connected would mean that there are no holes in it. And what's the formal definition now? Formal definition is all right, what's the formal definition? Every simple closed path that lies in D encloses only points of D, right? So for every simple closed path that lies entirely in D, every point enclosed by C is in D also. So it's saying if it's simply connected, no matter what, these are little closed paths now. No matter what little closed path C I pick, now the inside C is all points of D. So do you see how a simply connected region violates that? That I can find a closed path that doesn't have all points. What would that closed path be like?
Part of it be closing the circle that's out.
No, so the whole C has to lie entirely in D. So you can't make C go through that like that. So what would it be? Yeah, so I could draw it. So this is not simply connected because I can draw a path around here like this. Path C. And not every point inside of C is in D because I've got all this stuff in the hole. So this is simply connected. All one piece with no holes. Not simply connected. So this example here I'm showing is it's connected, but it's not simply connected, right? It's connected because given any 2 points A and B, you can get a path that stays in D, but not every closed path contains all points of D, right? So let's see what the implications of that are. So questions on connected regions or simply connected region?
I have one.
Yeah.
What if I check the number 8 that has the region count?
So first of all, the boundary of that is not a simple curve. Is it crossing? Yeah, so it's not a simple curve in the first place. But you could, potentially, you could just say that it's like tangent like this. So what, let's see. It's weird, let's see. So I think for sure it's connected. Is it simply connected? Yeah, I think it's still simply connected because it follows it doesn't violate the definition, right? Every closed path you could draw inside would contain only points of D. So yeah, but the problem is if this is truly an 8, then your boundary isn't simple in the first place, right? So your boundary isn't simple. It's yeah. Okay, sure. Other questions? Okay. So let's talk about Green's theorem and non-simply connected regions. So here's a typical. Is this connected? This region? Is it simply connected? No, right? It's connected but not simply connected. So if we wanted to apply Green's theorem to this, what we want to think about is let's split this in two. All right, let's split this into two. And then separate them, okay? So we're going to split this thing in half and then separate it. And then think about each individual line integral, each individual region, okay? So we're going to have our positive orientation, which means as we walk it, the interior is on our left, remember that? Okay? So if we were to then, so I'm going to call this, let's go C1, C2, C3, we'll break up all the pieces here, C4, and then C5, C6, C7, C8. Okay, so now if we were to compute the line integral of this thing, now that it's split apart, what would it be? It'd be C1 plus C2, the integral over C1, plus the integral over C2, etc., all the way up to C8. And what would happen? Do you see what would happen when we do that? What cancels out?
C3, 4, C1, 8.
C1 and 8 cancel out? What would cancel out? C4 and C6 would go away, right? These are equal and opposite line integrals. And also C2 and C5. Leaving what? So then in the end, we'd have integral of over C1 plus C8, which is what? What is C1 plus C8? Line integral of the outside loop, right? The line integral of the outside boundary. Plus what? C3
3,
and C7, which is what? The line integral the inside. Okay, notice, why isn't it? So let's show that. So when we put them back together, so we'll have to say, so I'll call the outside C1 and the inside C2, and so then for this region, the line integral C, f.dr, would be, so let's call this A and B now, since we already used numbers, A and B. Okay, it'd be the line integral over CA plus, now notice that B is clockwise. Is it correct that it's clockwise? Is that positive orientation?
Yes.
Why?
Because if you're on the inside, the left is going to be the opposite direction.
Yeah, see, so in this inside loop, in order to keep the region on our left, we have to go clockwise. Do you see that? And that's what positive orientation is. That's the bottom line is when you walk the path, the region has to be on your left. And so it's for a hole in a region like that, then that makes it a clockwise, or clockwise is positive, because then the region is to your left. Okay, does this make sense? Can I erase that stuff? What I've written? Okay, so using Green's theorem means C has two loops. To find the entire boundary of D is formed by two loops, not just the outside boundary, okay? So what would the line integral would be? The sum of the two line integrals. So I'm back to calling them C1 and C2 here. And that would equal our double integral of D over D. So now what happens in a conservative vector field? In a conservative vector field, what would equal 0? Does everything equal 0 then? So now we're looking at a non-simply connected region, and suppose we have a conservative vector field. Does everything equal 0? So each side equals 0, right? The double integral equals 0. And then the sum of our two single integrals equals 0. So what does that mean about the two integrals? Yeah, they're equal and opposite. They're not 0. They're equal and opposite. Okay? So does this make sense? If we're in a conservative vector field, then yes, the double integral over D is still qx minus py is still 0, so the double integral is 0. But now our line integral is the sum of the two loops to make the whole boundary. So then that sum equals 0, meaning that those two loops are equal and opposite line integrals and non-zero. Anybody have a question on that? Does it make sense? So now we have arrived back at our question. Remember, when we did this, we got that we had a conservative vector field, we did the blue square, and we got 0, just as expected. But we did the red circle, and we got 2 pi. Unexpected. Now we can answer this. Why is it 2 pi and not 0? Anybody see what's going on here? Yeah?
It might be non-simply connected.
Okay, so maybe our region's non-simply. Now we have a case where you get a non-zero integral if you have a non-simply connected region, but is it non-simply connected? So what are we talking about? We're talking about the region inside the disk, right? Everything inside the circle. Is it simply connected or not? It is simply connected? Look at your vector field.
Undefined 0. Undefined 0.
What's happening in our vector field? He said, dang it. I said he said. So, what's that, Alex?
Undefined at the origin.
Is it undefined at the origin? At 0, 0? So what does that do? There's a little teeny hole right there. Teeny hole. 1 point, but it's still a hole. So this is not simply connected, right? This is not simply connected. So if we really wanted to do the line integral for this region, what else would we need to do? We've got more to the boundary. So we have to do what? We have to do another line integral around our little thing. So let's call the radius of that A. Capital R. So the radius we'll call capital R. Okay, and so now we want to do and which direction are we going to go for that? We're going to go clockwise, right? Because we need to walk around this so that the region D is on our left. So that means clockwise, right? We're going to go around clockwise. And we're going to do, and we'll call that, say, C3. So we'll call that little thing C3. So now we need to find C3 FDR. Okay, it means we have to parameterize the surface. Sorry, parameterize the curve. So RT is, what would it be?
0, 0.
No, we're parameterizing this curve with a radius capital R. So we're just going to imagine this is just like a real small radius around that. It's going to be capital R cosine t, capital R sine t. So we can handle that with, so we could, or we can handle that with the limits. So I was just thinking we do the limits, right? So we go t could go from what? Yeah, you go 2 pi to 0, or you go 0 to negative 2 pi. So that would force it to go around clockwise. Okay, so then we keep going here. So what's f? Negative y is? Negative r sine t over. So what's x squared plus y squared going to give us if we do that squared plus that squared? Capital R squared, right? Because we have r squared cosine squared, r squared sine squared, that's going to be r squared, right? And then x is r cosine t over r squared again. And then dot dr is r negative r sine t and r cosine t. Everyone following what we're doing? And we're going to go from 2 pi to 0 is great. So we can start at 2 pi and go around to 0. It's one loop around. Okay, and what do we get when we do this? So we're going to go from 2 pi to 0. Is it just 1? The whole thing 1? R and r squared. So we just get 1. And what do we get? But now we actually also have to take what? We take the limit as capital R goes to 0, right? Because we want to get the whole region D. But the limit is capital R goes to 0. It doesn't matter, right? But to be precise about this, we want the infinite little, tiny little path around the point, right? So that means you take the limit of that radius as capital R goes to 0. It doesn't affect it. We still get what? Is that what we expect? Right, because now we got the 2 pi for the outer loop, negative 2 pi for the inner loop, and it works, right? So Green's term still works because it's conservative, right? We have that our line integral around the boundary of this D is 0, because we have the 2 pi from here, 2 pi plus the negative 2 pi equals 0. Which is what we expect for a conservative vector field. So what did we do wrong at the beginning? We missed all of the boundary, right? We only did some of the boundary, and so if we only do some of the boundary, we're not going to get 0. We needed to include this other part of the boundary too, so it worked out. Okay, was it a satisfying conclusion? Despite the yawns. Okay, so that's Green's term. So we're going to start the next thing. Any more questions on Green's term? So make sure you understand this for the final. I spent time on this for a reason, okay? So we want to understand this. Can I erase and go on? Last chance for questions. Cool stuff. It's getting good now, I'm telling you. All right. So we want to talk about rate of change of vector fields. Rate of change of vector fields. Because vector fields are kind of complicated, multidimensional things, there's actually 2 rates of change that we can think about for vector fields. So vector fields have kind of 2 types of rate of change. The first is what's called curl. That's rotational rate of change. What is a vector field again? It's a function of vectors, right? Either in the plane, it's a function of vectors in the plane determined by location, or vectors in R3 determined by location, right? So it's a function, so we can think about the derivative of it, but because it's a more complicated type of function, you put in a location and you get out a vector. Like I said, we got 2 types of rate of change. So the first type is curl, rotational rate of change. So I'm showing you a region C, or a region D, with a loop C as its boundary. And so we're going to look at, to understand curl, we're going to look at one little element, kind of like what we did with Green's theorem, one little element inside the region D. Okay, we're going to focus in on a little dA. Okay, and so I'm going to highlight that and blow it up. Okay, so I'm going to take that little dA, that little element, and I'll blow it up, and so it's like a rectangle with dimensions dx and dy. Okay, and so since that lives in the vector field, there's vectors here. So I'm going to call the vector at the top of this little element f of t, and the vector at the bottom fb for bottom, and then f left and f right. So this little element lives in a vector field, and so because there's a little change in x and change in y, there's potentially a little change in the vectors around it, right? Does that make sense so far? Okay? So according to the right-hand rule, positive value of curl, or positive value rate of change, will be counterclockwise, just like we said before. So counterclockwise rotation is going to be positive rate of change for this sense of rate of change for curl. Okay? So when you rotate counterclockwise, your curl is positive. All right, so now we got to figure out what is contributing here. We got these the forces around this, or at or around this little element. What's contributing to counterclockwise rotation? Okay, so we're going to look at the components of those 4 vectors. The horizontal component we call what? What do we call the horizontal component conventionally? For a vector field, the horizontal components, x components, P, right? We used capital P. So purple for P, P for purple, okay? And then the vertical components, Q, right? Q for green for Q, right? All right, so we broken up those vectors into their P and Q components. So let's talk about first the top and bottom. So first the top and bottom vectors. Which components of those top and bottom vectors contribute to twisting of this, or rotation? He says P. Agree with that? What about the Q components of the vectors at the top and the bottom? Do they contribute to turning or twisting?
No.
So you have to imagine they're applied right in the center. So the Q component, like this green thing, is applied right here, pulling up, and this one right here is right below, pushing up. Does it contribute to twisting? Do you see that only the P vectors at the top, the P components, top and bottom, contribute to turning? Ben, do you see that? Okay. All right, so watch this. So we're going to get rid of that one. Bye. And then bye-bye. Okay. All right, so we just want the P for the top and the bottom, okay, which contributes to the turning of this thing. All right. So what we're really looking at for rate of change then is we want how much does P change for a change in what? So how much does P change for a change in what? What's from here to here, what changes? Y, right? So we're interested in how much P changes for a change in Y. Right? So given a little change in Y, how much does P change? And so remember our old, for rate of change, dy equals m dx. So that's our rate of change. So what is the rate of change that tells us how much P changes for a change in Y? What is it?
P of ft minus P of fb.
Right, so then what's the rate of change, right? So what's the rate of change that gives us how much change in P we have for a change in Y? So basically, in asking the question, I'm telling you the answer. What's the rate of change? How much does P change for a change in Y? What derivative? So exactly what derivative is it? Partial derivative of
X. P.
P with respect to Y, right? So it's going to be the partial of P with respect to Y. That's the rate of change of the P vector with respect to Y, right? So because if we're going up like this, it's only those horizontal vectors that are going to cause rotation. So what we care about first of all is the rate of change of P with respect to Y. All right, now what about for the vectors on either side of this horizontally, left and right? So what are the components that are going to contribute to turning? Just the Q's. Okay, so we want to get rid of the P's. Ready? Watch. Okay, so we only want the Q's then. So then what is the as Q changes, right? We're going to have a change in Q for a change in X. And what's the rate of change? Yeah, the rate is going to be the partial of Q with respect to X. So it's the partial of P with respect to Y and the partial of Q with respect to X. Those combined together give us the total rotational rate of change. You see that? But if counterclockwise is positive, then what about the contribution of dp dy? That's turning us which way? Do you see that for a positive change in x, that dp dy is actually causing clockwise rotation? So it's giving us, it's fighting against counterclockwise rotation. So when we combine these two together, but Q, the change in Q for dx is giving us the rotation that we want counterclockwise. Do you see that? So when we combine the effects of partial p with respect to y and partial q with respect to x, what's it going to be? Yeah, so the partial q with respect to x, when it's positive, it gives us counterclockwise rotation, right? But when the partial of p with respect to y is positive, which I'm showing like in this picture, right? This is positive. It's going to give us clockwise rotation. So it's fighting against our positive curl, so we have to subtract it. Does that make sense? So that's our rate of change. That's the rate of change, rotational rate of change. And similarly, that's what we were looking at in Green's theorem, right? We're looking at the rotational rate of change in Green's theorem. And that's the curl of f. But curl is a vector. So what's the direction? If it's by the right-hand rule, then what is the direction of the curl? What's that? It's in the positive z direction, right? So if it's if positive rotation is counterclockwise, then by the right-hand rule, the actual direction of the curl vector is orthogonal to the plane of rotation. Do you see that? So it's z. So the curl of f is really, the magnitude is qx minus py, but the direction is orthogonal to the plane of rotation. It's k. You're not going to get this in any other Calc 3 class. Be lucky you're here. This is good stuff. They're just going to just tell you what the formula is, okay? So understand this. This is cool. All right, so then what about an R3? So then R3, instead of a two-dimensional element, you have a three-dimensional, like a little cubic rectangular solid, and you have rotation in all three planes. And so we're going to add those together. So just quickly, we'll just do we'll just do the YZ plane. So now imagine you have a three-dimensional element. Now I'm showing you Y is this way and Z is this way. Okay? So everything's the same as what we just did. But now Q is the Y is Q, and so this is like QL, and this is RL. So what's going to contribute to rotation in the ZY plane? So with respect to Z, what's going to contribute? Nope. DZ. So as Z changes, it's going to be Q, right? It's going to be Q bottom and Q top are the ones that are going to, with respect to Z, are going to give us rotation. And then similarly, with respect to Y, yeah, it's going to be the vertical components on to the left and right, or R. So, and then what will the direction of this component of the curl be? In what direction will this point? Positive X, right? Coming out of the board. So this is going to be, so the X component of the curl will be the partial of R with respect, let's see, where are you? It's the partial of R with respect to Y minus the partial of Q with respect to Z. That's exactly analogous to what we did on the previous screen. But this is for rotation in the YZ plane or in the X positive X direction.